net electric field. And you won't be surprised to see the equation here that vector addition to electric fields from multiple charges is just adding like vectors. We've seen this with forces, we've seen this with velocities, we've seen this with many vectors prior. We will add it like vectors. And such, we will add in the x direction separate than the y direction. And if we need to find a net electric field, we can use Pythagorean theorem and add those two components up together. We can also find an angle equivalently with trig as needed. Remember that signs arise from a coordinate system, and remember to always draw a vector diagram. There's no sense trying to keep all of that in your head. That's what the vector diagram is for. So I have this example here from the OpenStax text. If I look at this point P, there's an electric field from Q1 pointing radially away from this positive charge. There's also an electric field E2 from Q2 pointing radially away from E2. And both of those are at that point P. I won't draw these two lines in there. I don't think that is a productive thing to do. You're looking at the electric field at this point due to this charge, which is represented by this vector, and the electric field at this point from this charge, which is represented by this vector. When you add those together, and you can do a vector addition like that, this is the net electric field of those two things added together. And notice that it's tangent to the curve here. Here's the electric field line. Here's an electric field vector. Here's an electric field vector. Here's the net electric field vector here. Here's another point, P prime. They've done the same thing. The electric field from charge 2 is here. The electric field from charge 1 is here. When I add those two together, I get the net electric field, which is tangent to the curve of the electric field line at this point. So we're going to add them like vectors. We can add electric fields from multiple charges, and you've seen these pictures before. So this is the net electric field. In the middle, notice that it points away from the positive charge and towards the negative charge. If they're equal charges, you will get just an electric field horizontal in that direction, because the positive y from one will cancel out the negative y from the other and result in that. And you can see how the electric field will add due to different charge distributions. The simplest charge distribution is just a 1D situation where we have charges on a line. And you can see that's what's going on here. I just chose the last picture there and made a problem around it. It says charges Q1 plus 5.4 nanocoulombs and Q2 negative 3 nanocoulombs, 3.1, lie along the x-axis with Q1 at the origin and Q2 at plus 4 centimeters. So I'm going to draw a line in here. Here's the x-axis is along there. There's the x-axis. And here is the origin. I'm going to draw the y because this is the origin, just to signify that this is the origin. And this distance here, they tell us, is 4 centimeters. It says determine where along the x-axis the net electric field due to the two charges is 0. Okay, where is this 0? I mean, we're looking at this picture, and it seems like we would be able to figure out where it's 0. And I've had students say, well, it's 0 like in this region because there's no electric field lines. And that's not true. There's an electric field through this whole region. If I took an electric field meter of something and carried it through, it's like the gravitational field. Every place on the planet, at the surface of the planet, there's going to be a gravitational field. I don't draw all the field lines. I'm going to assume that there is a constant one throughout. So that's what's going on here, is there is an electric field here. But there's some point along this x-axis where there's an electric field equal to 0 total. The electric field from the positive adds with the electric field from the negative to cancel each other out. So this is how you solve this picture, and this is why I said draw vectors. Here's how you draw vectors for this problem. So I'm going to extend this down, and I'm going to divide this problem, this figure, into 3 different regions. All right. I have a region here, which I'm going to call region 1. In the middle, I'm going to call region 2, and over here, I'm going to call region 3. And sometimes you'll get a multiple choice. They'll say, where is the net electric field equal to 0? And you'd have to choose one of those. This is how you do it. Well, I look at the electric field due to charge 1 and the electric field due to charge 2, and I will add them up and have it equal to some sort of net electric field. This makes sense. Let's use blue for the positive charge here. The electric field lines point away, so in this region along the electric field line, it will point away from the positive charge. This is the positive charge here. It will point away from the positive charge in this region and also point away from the positive charge in this region, right? This is where the positive charge is. It points away in all regions, and that's the vectors representing those electric field lines, just the direction. If I look at E2, that's a negative charge. The electric field lines will point towards it. So maybe this is an easy region. The electric field line points towards the negative charge here. Well, over on the other side, the electric field will point in the negative direction there, towards the negative charge there as well. So we have the electric field lines all drawn out. And I ask myself, where would these add up to 0? The instinct would be in the middle, but actually you can see that they're adding in the middle. So this will not be equal to 0. This will be some value. So here they add up to some value. In this situation, they subtract, and in this situation, they subtract. You can see that they're pointing in two opposite directions. So we've narrowed it down. It can't be in region 2 because they're adding together, and we want it to equal 0 overall. So we want to have them pointing in opposite directions. Over in this region, region 1, I'm going to say that the electric field due to the positive charge, notice in this situation, the positive charge is larger than the negative charge in magnitude. This is 5.4 and this is 3.1. So there's no way that the electric field due to the negative charge is going to be larger or equal to the electric field due to the positive charge in this region. The positive charge will always be larger. Just because it's a larger charge, it will always have a larger electric field in that region, and so it won't add to 0 in that region either. So in this region, this is where they're going to add up to 0. E net equals 0, so I'm going to have the electric field due to 1 plus the electric field due to 2 equal to 0. And we're going to get E1 minus E2 equal to 0. And we can see that the electric field due to E1 is going to be equal to the electric field due to E2 in magnitude. Okay, so just setting that up and being formal about it. You may have multiple charges, 4, 5, 6 of them, and this may be a useful thing to do. So the electric field, let's set up an equation now. Now that I have the electric fields equal to one another and I've identified the region, we're going to have to go KQ1 over R1 squared and set that equal to KQ2 over R2 squared. Okay. What's R1 and R2, or what do we want to solve for here? It seems like R1 and R2 are both unknown. I have this point P. I'll call this point P here. That's where this electric field is equal to 0. E equals 0 here. And I can see that R1 is going to be this, R1, and R2 is going to be 4 centimeters less than R2. So I'm going to write that down. 2 equals R1 minus 4. It's smaller. It's a smaller value. Okay. It says determine where along the x-axis the net electric field. So actually we're looking from the origin, we want to find R1. So that's what we're looking for, is R1 equals what? So I'm going to plug in an expression for R1 into for R2. And I'm also going to do some algebra. I'm going to get rid of this K. It's in both terms. I'll just cancel it. I'm going to move the Q's together as well in order to have a ratio. So I can put R2 squared on this side and say Q2 over Q1 R1 squared. There's some algebra there. You can double check if you like. And the convenient thing to do here, I'm going to square root both sides. I can see that R2 equals the square root of Q2 over Q1 R1. You may have put in this expression R1 minus 4 squared equals Q2 over Q1 R1 squared and then FOILed this out. You may do that algebra, but it's not the quickest way. I'm not saying you won't get the right answer, but this is definitely not the quickest way to get this answer. The easiest way is to do it this way. R1 minus 4 equals to take the square root first. So when I solve this equation for R1, I get what do I get? I move this over here, the 4 over here, divide by on both sides. I get 4 over 1 minus the square root of Q2 over Q1. And you can check my algebra if you'd like to do that. We can plug in what we know about the charges. And I'm leaving this in centimeters because I'm not forced to. I'm not using that value for anything. It just wants a distance. And I assume it's going to be larger than 4 centimeters. So when I do the ratio of the charges, the nanos are going to cancel. You could put the nano in times 10 to the negative 9th. But that'll cancel in the top and bottom. So you can just put the ratio of 3.1 over 5.4. One thing I will caution you to do is don't put the value of the charge in there. You don't need to put the negatives and positives in there. This should be just the absolute value of these two things in here. Remember, we've already decided the direction of the vector, and that gave us the value, the signs in the coordinate system up here. I already took the positive and negative into account there. Down here, I just entered the value of the charges. When you run this through your calculator, you will get R1 equals 16.5 centimeters. And that will be the answer for that question. So net electric field, we see that we're going to do some vector addition. I'm reminding you to draw the vectors here. Make sure you're drawing out these vectors so that you can see them, to conceptualize what are you adding and subtracting, where are they adding and subtracting. I've chosen another example for us to practice net electric field. Here's another 1D1. A uniform electric field exists everywhere in the xy plane. This electric field has a magnitude of 4,500 newtons per coulomb and is directed in the positive x direction. A point charge, negative 8 nanocoulombs, is placed at the origin. Determine the magnitude of the net electric field at these 2 points and their equidistance away from the charge at the origin. So I'm going to get a picture going here. Here's the positive x direction. And then here's the origin here, and I'm putting a negative 8 nanocoulomb charge there. So that's where that is. It also says there's a external electric field, and let me get this line straight here. Here's the external electric field, which is everywhere in this region. Everywhere in this region there's this external electric field. I'll call this E external. And what they want us to do is find the net electric field at these points due to the electric field of these two things. There's an external electric field, and then also I'm going to note that there's an electric field due to the negative charge. So let's see, there's this point here and this point here. This is for A and this is for B. And they tell us that the distance here is 0.15 meters on either side. So for A, and what I'm going to do, and remember what I said was draw the vectors. So when I think about the negative charge being here, the electric field is going to point in this direction towards the negative charge at A and towards the negative charge at B, so the opposite direction. I've chosen another example for us to practice net electric field. Here's another 1D1. A uniform electric field exists everywhere in the xy plane. This electric field has a magnitude of 4,500 newtons per coulomb and is directed in the positive x direction. A point charge, -8 nanocoulombs, is placed at the origin. Determine the magnitude of the net electric field at these 2 points and their equidistance away from the charge at the origin. So I'm going to get a picture going here. Here's the positive x direction. And then here's the origin here, and I'm putting a -8 nanocoulomb charge there. So that's where that is. It also says there's a external electric field, and let me get this line straight here. Here's the external electric field, which is everywhere in this region. Everywhere in this region there's this external electric field. I'll call this E external. And what they want us to do is find the net electric field at these points due to the electric field of these two things. There's an external electric field, and then also I'm going to note that there's an electric field due to the negative charge. So let's see, there's this point here and this point here. This is for A and this is for B. And they tell us that the distance here is 0.15 meters, 0.15 meters on either side. So for A, and what I'm going to do, and remember what I said was draw the vectors. So when I think about the negative charge being here, the electric field is going to point in this direction towards the negative charge at A and towards the negative charge at B, so the opposite direction. When I look at adding these vectors in these different regions here, when I think about adding the vectors at these two different points, at point A, the E net is going to equal the external electric field, E external, plus that electric field due to the negative charge. They're both pointing in the same direction and they're going to add together. At point B, the net electric field is going to equal the external electric field, and it's pointing in the positive direction. This one's in the negative direction, so minus that electric field due to that negative charge. So if I had values, I could calculate this. I still need to calculate E negative here, and I can do that over to the side. The electric field due to that negative point charge is going to be K, 8.99 times 10 to the 9th times the charge, which we know is 8 nanocoulombs, so that's 8 times 10 to the -9th, and we're going to divide by the radius. The radius in both of these situations is 0.15, and that's why I'm thinking about them at the same time. So this is 0.15, and remember to square that. I see students dropping the square. Remember to square that. When you solve for the magnitude of this electric field due to this -8 nanocoulomb, the magnitude of it, remember this is the magnitude of it. I'm using the magnitude of that charge up here. The magnitude is 3196.4 newtons per coulomb, and that's a repeating force, so that's that value. So now that I know that, I can plug that in these two situations. In this situation, this vector, these two vectors add, so I'm going to get 4,500 plus that 3196.4. Over in this situation, I'm going to get the 4,500 minus that value, 31964. And that allows me to calculate these values. I get 7696 newtons per coulomb over at point A. And over at point B, I get 1,304 newtons per coulomb. So that's the answers for those two problems. What I'm going to do is the next problem has us look at a different point. So I'm going to keep the information I have here, except I don't need the equations. And I'm going to move it to the next slide. So on the next slide, we have a different situation. It says the uniform electric field and everywhere 4,500. We have the same situation. It says determine the magnitude of the net electric field at y equals +15 centimeters. Okay, so in this situation, we have y equals. Before we had x equals, but now we have y equals. This is the y-axis. And they want us to look at a point up here, point C. Okay, so at point C, the electric field, due to the negative charge, isn't pointing left or right anymore. It's pointing downward. There's the electric field due to that charge. And now you can see why I chose this example. It's a 2D example. We're going to add the two electric fields as vectors, right? We'll say E net at that point has to equal the external electric field, which is a vector, plus the electric field due to the negative, which is a vector. And you can't just add them or whatever here. They're at a right angle. So let me draw this. We'll draw 4500 at this angle. Here's the 4500, the E external. I'll call this E external. And we also have the electric field due to the negative charge at the origin pointing downward, and that's the 31, etc. Okay, so I'll call that E negative. When I add those together, they're going to add like vectors, so we're going to do vector addition and get this vector here, which I am going to call E net. And you can see how Pythagorean theorem and using trig to find an angle will be the appropriate thing to do in this situation. So E net, when I find the magnitude of E net, it will equal E external squared plus E negative squared, take the square root. And we can put values in there. You can see the values here. When you run this through your calculator, you will get the magnitude of that net. You get 5519 something, which I rounded to 5520 newtons per coulomb. We can find that angle theta. That angle theta is going to be the inverse tan of the opposite over the adjacent. So you can see that the opposite is going to be the y component and the adjacent is the x component. So we'll go E negative, which is the y component, over E external. Those are both numbers that we know. We have both of those numbers. And when you run that through your calculator, you get 35.387 degrees, and I'm going to call that below the horizontal. Below the horizontal there. It extends below the horizontal. Relative to the x-axis might be another way to say that. So that's how I would add electric field that were perpendicular to one another. Very straightforward with Pythagorean theorem. I chose another point on the next slide in order to look at. So let's bring our situation down along here. It says a uniform electric field, 4,500 newtons per coulomb, everywhere in the positive x direction. So same situation there. But I chose a different point. X equals plus 0.5 and y equals plus 0.5. Okay, so now we're actually at this point here, point D. Point D has a different radius than the other ones. All of these were 0.15 meters. This one has a different radius. You can see that here. And the electric field due to the negative charge is going to be pointing towards it in this direction. And it's a square, right? 0.15, 0.15. So when I draw that vector, and I'm going to draw that over here, right there. When I draw that vector, I know this is a 45-degree angle, and I'm going to call this E negative. At point D, I'm going to be adding it with the external electric field, which is the 4,500, so E external. Because I have a new radius, I have to calculate a new electric field for that negative charge. All right, I'm still going to have point K times 10 to the negative 9th. I'm still going to have the Q, 8 times 10 to the 9th. Both of those are still there, but I'm going to have a new radius. The new radius is going to be the square root of 0.15 squared plus 0.15 squared, which is 0.15, the square root of 2. So that's what you would plug up here, 0.15, the square root of 2, quantity squared. And when you calculate this electric field due to the point charge at the origin, you will get 1598.2 newtons per coulomb. Notice that it's less than when it's at point A or point B or point C. We got the 3196. This is less than that. So 45-degree angle. So now we're adding vectors. And we can do this when we add vectors. We add head to tail. So let me draw the other vector in here a little bit better. So there's the net electric field. That's what it's going to look at the after we add E minus to E external. That will be the net electric field. The easiest way to do this, E external is in just the x direction, but E negative has components to it, and you can see that here. And I can divide it up into like an EX and an EY. And the easiest way to do this, if you're wondering how to do this to make it easier, is with a chart. You could do this with a chart. You could just straight write it out, and that would be fine as well. So I will take my two different electric fields, and when I add them together, they will equal E net. And what I will consider for each of them is their x component and their y component. So when I consider the x component of E external, I definitely have 4,500, and that's it. When I consider the x component of the negative charge, I'm going to have 1598. The 1598, the magnitude of this vector, times cosine 45 degrees, and also in the negative direction. Notice that's pointing in the negative direction. So that when I find the net electric field at that point due to these two vectors adding together, right? One's in this direction, the other's in that direction, one's smaller, we get 4,500 minus the 1598 cosine 45. So that's going on in the x direction. In the y direction, the external electric field has no y component, and the electric field due to the negative charge is pointing downward. It gets a negative sign, and again, it's 1598 sine 45. It's the opposite leg, so it will have a sign to it, and that is the net electric field in the y direction. It only has a component due to the negative charge. So that will be our net electric field. When I look at it, this will be 4,500, and when you calculate this value, it will be 3369.9 newtons per coulomb, and this value will be 1130.1 newtons per coulomb. That is the net electric field. It has these two components, and that comes from here, and that comes from here. I can find the value of that net electric field then. I will use Pythagorean theorem in order to find the value of E net. E net, when you use Pythagorean theorem in here, so I'll put an absolute value around it, it's 3,554 newtons per coulomb. And I can also find that angle. The angle will be the inverse tan of 1130.1 divided by 3369.9, and when you run that through your calculator, you're going to get 18.5 degrees below the horizontal. So that's how you would add electric fields in a 2D situation. Divide them up separately into their x and y components, add the x components, add the y components, and then you can use Pythagorean theorem in order to add them together and use trig to find the angle.